This is a picture of the curve of binding energy, which is, I purposely used the title of a book by John McPhee. Do you guys read Bill Bryson? Do you have any Bryson fans here? John McPhee is one of these scientific writers like Timothy Ferris, and Bill Bryson is not totally a scientific writer, but he could write about washing machine repair and make it just riveting. That's probably not the first book to read, The Curve of Binding Energy. I would read Coming into the Country, where he goes up into Alaska and just sort of basically does a snapshot of these crazy people that have moved to Alaska, and some of them are, bulldozing stream beds looking for gold, and hydraulicking, which is where you use high pressure water. Water is going so fast that it burns you when you touch it. Like, think about that. Okay, but the whole point of his book of The Curve of Binding Energy is that the government is being fairly lackadaisical about the dangers of nuclear fission, and the primary danger, he thinks, is that it creates plutonium. And plutonium can be easily made into an atom bomb. Plutonium can be easily made into an atom bomb. Uranium, not so much. Uranium-235, the technical challenges are pretty high. But if you gave me enough plutonium and some plastic explosive, this is all I would need, okay? I could go to Home Depot, and I will show you today how to make a nuclear weapon. Now, it's not going to be a great one. It's not going to achieve any efficiency that's very high, but it definitely would put a dent in Manhattan. And if plutonium doesn't explode, it just gets scattered everywhere. Yeah? Right? And that's good, because plutonium is like one of the most poisonous things on Earth. It's just this incredibly toxic thing, and so yeah. But anyway. Okay, so this is the curve of binding energy. This is, remember what this means, okay? Things that are high up on this thing are stable, yes? This is the most stable thing. These are the most inert things. And when you go from ert to inert, you release energy, correct? Okay, so the most ert thing we've got is hydrogen, right? Yeah? And the biggest reaction we can get is we can turn hydrogen to helium. This is nuclear fusion. We are fusing things together, right? This is what the sun does. This is what stars do for most of their life. And the reason they do it for most of their life is that's where most of the energy is. And then, of course, once they've made helium, they can make things like oxygen, right? And that releases some energy, yeah? Doesn't it? Right? And then oxygen, if it's a huge giant star, can take things like oxygen and carbon and make them into things like iron. And then stars sort of, they can't get any more energy out of putting stuff together. And that's what stars do, because they're pressure. They make pressure, right? And you need pressure for fusion, because the nuclei don't, like each other. They're positively charged, right? What we did, what we're doing right now, our nuclear power, we can't do that yet, okay? But we can do this. We can take uranium and we can split it up and release energy by moving this way on the curve, right? But these things are the most stable things on there, right? And then we've talked about that fusion. So this is fission. If we take things like this and we split them, we release energy to make things more like radium, or ultimately like iron or whatever, right? So that's the most tightly bound. On this side, label that fission will release energy, right? And on the other side, fusion is going to release energy, right? So this, if you make bigger nuclei than this, you release energy. If you make smaller than this, you release energy.
How old is that cup?
20 years old. It's definitely 15 years old. I had it before kids. So. Do I need a new cup?
No.
I know. It's a coffee people cup. So define binding energy per nucleon is just the total binding energy divided by the number of nucleons, divided by the mass number. What's more or less stable? Well, these guys are the most stable. Anything below that is less stable, right? So most stable, less stable, right? You could label it that way, right? Yeah, okay.
Total binding energy divided
By the mass number.
So, boom, going back to the graph.
Yeah.
Did you take the uranium and split it up? If you go past iron,
Yeah, yeah, definitely in a fission reaction, going past iron actually stores energy, right? It doesn't release energy, right? Which of course, I don't know if you're wondering this, but if stars stopped making in their normal life atoms or nuclei at iron, how did uranium get made? Yeah, supernovas do it, right? This is the catastrophic gravitational collapse of stars. Right. Yeah, basically. So when you see Mount Hood, okay, in the distance, as you drive home tonight, I don't know, right? When you see it, right, know that the energy that's driving Mount Hood is the radioactive decay of nuclei deep in the Earth's core, right? That was stored there by the catastrophic explosion of some star before our solar system was made. It's just kind of interesting. So here's the atom, right? And what are the forces in the nucleus? Well, there's the Coulombic force, which is tending to tear apart the nucleus. Ultimately, the Coulombic force is what determines the ultimate is going to rip apart these nuclei. When you look at the periodic table, there are these uniquardium or whatever these things are, right? Okay. Where are those guys? Anyway. Yeah, there we are, right? Those really short-lived things with like the mass number in parentheses, they don't even know how many nucleons they put together to make it, right? They have no clue, right? Because they're around for like a billionth of a second, right? There's just, it's gone, right? Okay. Those things the thing that tears them apart is the Coulombic force, okay? And it's the strong nuclear force that holds it together. And remember that the strong nuclear force is a very short-range force. Why is it a short-range force? Well, we can do a simple calculation, but it's bizarre. Space itself is unstable, is quantumly uncertain. Space itself is quantumly uncertain, right? So the things that mediate these, what is this, h bar over 2 or something like that, right? Okay. So space itself, the thing that mediates these forces, okay, are these little virtual particles. So the electrical force, right, is mediated by photons. The strong nuclear force is mediated by much more energetic particles. So if this is big, what must be true about the time they can exist? Is small, right? Okay. So if the energy of the particles is big, and they have to be big because it's a big force, right? Okay. So if these are energetically very large, they can exist for very short times. The fastest they can go is the speed of light, right? Yeah. They can't go faster than that. Okay, and so that makes them a short-range force. The strong nuclear force is short-range just because it is so strong, right? It doesn't, can't emanate very far. And so here's the deal, right? Since it's so short-range, as the nucleus gets bigger, the one side of the nucleus has difficulty communicating that force to the other side. Some of the particles that you're adding are out of range of the nuclear force. The Coulombic force, though, is very long range, yes? We saw it acting over spaces of meters in this room, didn't we? We saw like things being attracted and repelled, right? Okay. So as the nucleus gets bigger, the strong nuclear force gets weaker because it's acting over such a long distance. The Coulombic just monotonically gets bigger. It doesn't care about 10 to the minus 15th meters of space, right? Okay. And so that's why you've got this graph. There were originally, as you add a proton, you add a neutron, add a proton, add a neutron, add a proton, add a neutron for the lighter elements, right? Somewhere along about proton number 20, element 20, right? You start to have to add more neutrons. Why? Because neutrons add, but they don't add, They don't add to the Coulombic force because they have no charge. They do add to the nuclear force because they are nucleons. Neutrons are attracted to protons, attracted to neutrons by the strong nuclear force, but they don't add to the repulsion of the atom, right? So if you look at this little graph here, it's almost, it's kind of an interesting curve there, right? And then what's going on up there? Why can't we just keep going? Why can't I just keep adding neutrons? It's too big, right? It's just the nucleus has gotten too big. The Coulombic force is still acting on it, and it's like, do you guys see The Meaning of Life by Monty Python? Yes? At the very end, they feed him a dinner mint, and that's enough to make him explode. Really gross scene. I was very grossed out by that as a high school student. Yes?
But you hear, there's this one element further along,
Uh-huh.
25 or something,
Uh-huh.